All right. So Tensordyne is an AI inference systems company. And so if you look at the theme of the conference yesterday and today, there are two main elements that are getting discussed. One is that the near to medium term, we have some significant power constraints. And then the second one is that if you look at the news for the last many weeks, many companies that are building agentic workloads and even model companies are not running profitable businesses. So the economics of AI matter, and the constraints on power need to be alleviated somehow. So we have to think about how to do that. Now, if you look at the AI playbook for the last 2.5 years from the ChatGPT event, there are basically the themes are around scaling laws, right? There are 3 scaling laws that are in play, right? There's basically pre-training, and then there's post-training, and now we have test time scaling. But what are the implications of all these scaling laws that are affecting and coming into play as we build better and better models? Well, the effect of all of that is an insatiable increase in the demand for inference compute. So we started about over a year back. It was LLMs were the theme, the interest, the point of activity. And then we went forward and we went to more fine-tuned models, mixtures of experts, reasoning models that take a significant amount of more time in thinking and reasoning. And those tokens cost money too. And then in the world of agents today, where you will chain many models together and consume more and more inference. And then if you look at conversations from yesterday, they're trying to build companies in this space, right? Infrastructure companies are trying to build systems for real-time high-definition video. So all of these are putting incredible pressure on the infrastructure that's getting delivered and built over the next few years. Well, if you look at the power required over the next few years, and we have let's think about a little bit of variability in the power required over the next few years, that has to follow that demand slope. That has to follow the slope of the inference demand. We do not, as an industry, all of us who are trying to build products for this industry, do not want to be in a situation where we're constraining the market, constraining the demand for AI just because we don't have power. And the projected power growth, if you look at, let's count from 2013 to 2023. In the US, the power generation capacity was about flat for a whole decade, just 2 years, till 2 years back. And what has happened since then? Microsoft has gone to 3 Mile Island and said, let's reanimate Unit 1 of a nuclear power station that was mothballed. Can you believe that? We look at gas turbines from GE or Nova. Their orders are out till 2030. There's no capacity left. There's news of somebody taking down and stripping down a power generation capacity somewhere and bringing it by ship and re-putting it and putting it back in the US. So all of these are fundamental. I would define it as almost like a power grab. So I grab as much power as you quickly can to build out your data centers. So this is a fundamental challenge that the industry faces. And so this power limited window, there's some variability in it, but it's if we plot the curve for AI inference demand over the next few years, we expect that we will hit that. So how do we solve that as an industry, right? How do we make that not a barrier to ubiquitous use of AI? Because all of us in the infrastructure business want to sustain this business. We want to grow that business. And if we want that to happen, we want more consumption of AI. We want broader consumption of AI across the globe. Well, if there's better AI, if models are better, and if we want agents to operate more effectively, the models have to be better. So if you look at the news from yesterday, Microsoft and Anthropic are collaborating so that Anthropic's Cloud Sonnet 4 model is going to be the underlying model for Office 365 Pilot. Or Copilot. So if you think about that, what does that mean? That these agents cannot sustain and operate with models that are mediocre or poor. You need models that actually can deliver value so that the agents actually give you substantial additional value as end users of those agents. So now, if we hit a compute roofline, we are constrained. And that roofline is imminent. And so if you look at the reaction of some of our vendors in this industry, the answer is, let me stack more and more reticle-sized dice together. Let me jam more and more of those chips on a board. Let's go from 30 kilowatt racks to 120 kilowatt racks to 200 kilowatt racks to 600 kilowatt racks. Great. So you're delivering more AI, but you're also saying that I'm going to drop your precision down to 4-bit. Well, what are the implications when somebody wants to run Sonnet 4 or ChatGPT or GPT-5, and dropping precision has implications on the performance of agents? So one has to think that it's not enough that you get enough petaflops out of the machine. The petaflops have to be valuable. They have to be usable at higher precision if you can. So what do we do at Tensordyne, right? We are defining a new scaling law. This new scaling law is, we define it as a zeroed scaling law. This scaling law underpins the other 3 scaling laws that I showed to you earlier. What does that mean? You want to go back to first principles, and you want to think about, how do we do AI? Well, what's AI? Most of AI is matrix operations, matrix dot products. We all hear the term matmos, or think about multiply, accumulate. Well, what if you can go back and think about the math fundamentally differently? Can you start from first principles and you think about the math radically differently and you approach it in a different manner? Well, if you can, maybe that might help alleviate all the other challenges that are in front of us. Alleviate the power challenges, alleviate forcing everybody going from higher position down to lower position and getting poorer quality models. So we think at Tensordyne that the breakthroughs in innovation AI will come from math. We know that, right? We spend a lot of time in math, all of us together. Well, what if you can think about approaching this using logarithmic math? Well, if you have logarithmic math, what is AI fundamentally? I described it as significant trillions, quadrillions, quintillions of matrix multiplications and additions that happen when a model is run. So when you take those multiplications in the log domain, they become additions. Multiplications become additions, and then going back to additions is difficult. And at Tensordyne, we've fundamentally solved how to do log math for AI. Actually, the chief scientific officer of the largest infrastructure company says that the most elegant way, I'm paraphrasing him, the most elegant way to do AI is actually using logarithmic math. There are some wonderful properties of logarithmic math in terms of continuous patterns of data that you can actually do AI pretty effectively. Well, if you do that, you can alleviate the power constraints that are in front of us over the next, say, half a decade, or maybe 6 to 7 years. And when you do that, there are additional benefits that accrue, operational benefits and cost benefits that will accrue that I'll show you in a moment, that suddenly unshackle this potential barrier that's in front of us, where we can't do more AI. We cannot make AI more ubiquitous. We all collectively, as an infrastructure players and collaborators and engineers, we want more AI to be used around the world. Let's look at an example. Microsoft Azure has over 120 regions and over 400 data centers. Amazon AWS has over 100 data centers. All those data centers around the globe cannot become liquid cooled overnight. Cannot deliver in those data centers, those racks do not have 100 kilowatts, 200 kilowatts per rack. But we as an industry want all those data centers around the globe to have models delivered and on that infrastructure around the globe. Well, with Tensordyne technology, we believe that can be possible. So let's go and understand logarithmic math. And by the way, if you look at log math, we were inspired by nature. So what does that mean? Well, if you look at nature, all living creatures, at least I believe all living creatures are intelligent, right? Whether it's your dog at home or whether it's a fish that knows how to swim and move, right? All living creatures are intelligent. But they can only sustain themselves with the amount of food and energy that they get by consuming that food and then being very efficient about how they function in the world. Well, that means that the metabolism of these living creatures, including all of us, we will have to go for lunch soon so we can sustain ourselves in the afternoon, right? Then you look at log in nature, whether it's a seashell or whether when we look at earthquakes and we refer to it in the Richter scale. Richter is a log 10 base scale, right? That is that if you go from an earthquake at 7 on the Richter scale to 8, it's 10x stronger. Well, how do we function in this world? So let's look at a couple of things, examples. Let's look at sound. From a pin drop to a sonic boom. That's the range of sound that we can sustain and deal with. Or if you look at light, if you go to the deepest caves around the world, you can barely see your hand in the darkness. And then you come out into bright sunlight at noon. Well, the source of all our energy and life on the planet is because of the sun. So the range is pretty significant. And what do we do? What does our brain allow us to do? We operate in that nonlinear world, logarithmically. So fundamentally, nature was an inspiration for all of us at Tensordyne. And we thought fundamentally that if we did the math differently, we could bring advantage to the industry. So let's look at a couple of examples. If you take a couple of chips built in the same geometry, let's take 3 nanometers as an example. For the same unit area, millimeter square of silicon, you can assume you can do about 10 teraflops of FP8, and you can get some amount of utilization. And I'll describe why that utilization number is low in a moment. And then you take a Tensordyne solution, we can do 4 times the teraflops for the same area in the same geometry of silicon. And you can get a higher utilization. So one asks, how can this be possible, right? How can you, for the same area of silicon, be transformative and deliver more compute for that amount of area? Well, if you look at the traditional approach that most of the industry does in doing AI, they use floating point 16, IEEE, or B float 16, or now they are describing FP8 or NVFP4. They're performing multiplications. Multipliers take area. Adders take less area than multipliers do, maybe 20x less area. So, yeah, I'm simplifying how log math's done. It's not. It requires significant engineering work because there's a challenge from going from linear to log. That's easy. You can multiply two numbers by creating an adder and adding them in log. But going back from log to linear is an incredibly difficult problem. And if you want to do that, and you do it brute force, you will lose all the gains that you got by going to building adders. So you have to fundamentally solve that. The other challenge is that there's a ratio rule between compute and memory. These compute engines require to be fed with activations and weights. Now, if you think about it, there's only so much real estate in silicon. In an 800 millimeters die, how much do you dedicate for compute? How much do you dedicate for memory? If you use a traditional FP16 or FP8 approach where you're building with multipliers, you have to dedicate so much of the area to the compute that you're left with limited area for SRAM. So the ratio of compute to memory is kind of imbalanced. Well, in our case, we're able to actually balance the ratio of compute to memory. So we're able to boost up the amount of memory so that we can keep the compute more busy. Because it's essential, right? Nobody buys an 800 horsepower car and then drives it around assuming that you'll get only 400 horsepower. Well, we all, as an industry, are obligated to our customers that if you deliver a certain amount of performance, we claim that we will deliver the performance, they need to get it, right? It's essential to think about it that way. So our ratio rule of compute to memory now gets to be more balanced. So when you balance it, the SRAM, which we define as near memory, now is able to deliver data at the insatiable compute demand of that compute engine. And that's why the utilization goes up significantly. Now, it's necessary to do this, but it's not sufficient. So if you think about a system for inference, you have to think about 4 critical elements. One is efficient compute. And this is where Tensordyne's log math approach gives us the highest compute density in the world, right? So you're able to deliver maximal tokens per unit of power. Then you need SRAM, enough capacity, enough bandwidth SRAM to sustain that compute, to keep it fed. So you're able to do that. Why? Why are you able to do that? Why are you able to put more SRAM with more bandwidth? Because your compute takes less area, consumes less power. The beauty in silicon is that if compute takes less power, SRAM doesn't take much power at all. It only takes power when you try to read the SRAM. So net, these two actually benefit each other mutually. But these were necessary conditions. They're not sufficient. You still need large capacity HBM because the models, the parameter counts are going up. Even with mixture of expert models, these models actually are large. A DeepSeek model is almost 700 billion parameters. You need to hold the model because you don't know a priori which expert is going to get called. So you checked off 3 boxes. You're not done yet. Models no longer fit on single devices. If one were to look at GPT-5 or Claude Sonnet 4, most of these models, including the GPT OSS 120B, run most efficiently on 8 processors or 8 GPUs. So you need now a scale-up network or scale-up interconnect. So if you don't solve for all 4 simultaneously, you're left high and dry. So at Tensordyne, we solve for all 4 of these. It's essential to remember you have to solve for all 4. Well, we have developed 3nm silicon that has 256 megabytes of SRAM that keeps our compute engine that's running in log math very busy. We have 144 gigabytes of HBM3E that can hold the largest models. And we also have dynamic automated microscaling capabilities in our silicon. But more importantly, we also have one of the world's highest scale-up interconnect. What does it mean? We can connect 144 of our accelerators seamlessly with a terabyte of bandwidth, bidirectional bandwidth. And so now our customers, the model creators, the model users can run any level of tensor parallelism. They can go from tensor parallelism of 8 to 144. They can also run any number of experts, unconstrained, unshackled. They can do 384 experts. They can do 512 experts. They can actually partition the system for disaggregated inference. So they can choose a number of devices for prefill and a number of devices for decode. Complete flexibility. Why? Because every accelerator of ours is equidistant from the other, any to any, and a single hop connection at the lowest latency. So now, what does it mean when you build these things? What does it result in? It results in the most efficient inference system on the planet. In a single rack, we can do 3 million tokens per second of Llama 70B. This is at 1/3 the capex versus the highest performing system today available in the market at 1/8 the power of the highest performing system in the market. So what did we do? We solved two problems at once. We delivered systems that consume much less power. So imagine a token factory, 100 megawatt, 200 megawatt token factory. We can actually deliver more tokens out of the factory for the same amount of energy. We alleviated the energy constraint in the short to medium term that we might see around the world. Secondly, we made the economics of inference far cheaper, both from a CapEx and an OpEx perspective. So the model providers can run economic business, and the agent providers can also run an economic business and be sustainable, because we want them to thrive. We want the agentic workload market to sustain and grow rapidly. We obviously need to build the software so that customers can take our models and run the software with a front end, and without much effort, compile and deliver the model. So we have familiar interfaces like Triton and PyTorch. Well, I just gave you a 70 billion parameter example, but let's talk about how well we perform across multiple mixture of expert models like a DeepSeek, 3x better than NVL72, a Llama 405B, 6x better, and the ability to get real-time HD video, like 4K video. All of that will be capable in our system. We would be the only vendor that gets more tokens per watt of energy compared with the rest of the industry. And in this chart, though we are not naming all the other vendors, the GPU vendors are known to you, and the startups are known to you that are advertising the fastest tokens of the world, but not listing out the number of concurrent users on those machines. So again, it's important to understand nobody will squeeze more tokens per watt in the industry versus us, because we fundamentally changed the math. CapEx. The CapEx benefits are also substantial, because when you build chips that are smaller, that consume less energy, you can pack more of them, and you don't even have to jump to liquid cooling. That means that now our systems can be deployed across the globe. So let's now bring it back to basics. When I started the conversation, I talked about the intermediate range, let's say next 5 to 7 years, power constraints that we have to alleviate. And then the economics of agentic, and in the world of agentic workloads and reasoning workloads, where you spend a lot more time thinking. So fundamentally, we solve it by starting with the math, building the silicon, building the system, and solving the data center challenge. So a combination of all these things makes that possible. Well, how do we show this to you? So please come by our booth in the exhibition hall. We have a calculator, because it's essential that neoclouds, hyperscalers, model developers come and understand the cost of delivering inference, not the price, the cost. How much does it cost for me to pick vendor A versus vendor B versus vendor C? So our calculator, we are using publicly available data, can allow you to do a tokens per second, vendor by vendor comparison, tokens per US dollar, vendor by vendor comparison, tokens per kilowatt hour, vendor by vendor comparison, relative cost contributions, number of racks. Let's remember, data center rack space is not for free. If you take more racks, then you don't have racks for other things. So it's essential that you look at this holistically. So what are we? We're Tensordyne. We have reinvented AI math. And that means that we've redefined AI inference. Because fundamentally, if you hear the story from this morning, we're in the world, in the theme of inference. The use of AI is inference capacity, inference demand. And so we are in that world. And so if you don't solve that world correctly, and if you don't solve those solutions needed for the customers, you're not going to get the rapid adoption of AI. So as a community, as a set of infrastructure players, it's our obligation to the higher layers of the stack to deliver the capability. We will announce our product next year. And so we'll welcome the industry, the press, the analyst community, even our competitors to come and visit us next year when we announce our product. One thing I want you to take away. We will be the only other vendor that will sell publicly, not captive, publicly, a scale-up system that can scale up to 144 devices in a system, in a scale-up system, which means that we can deal with the largest models in the world, no matter the scale, no matter the number of experts, no matter the performance demands of it, and delivering it at the most efficient cost at the most lowest amount of power. Thank you very much.